Dear audience, I want to begin by expressing my deepest gratitude for your interest in this topic and for joining me once again on this journey through knowledge and exploration. Your warm participation and the precious time you give to my videos means more to me than words can describe. Every moment you spend watching, supporting, and engaging becomes an honor for me, a true gift that I value with all my heart. Your sharing, your liking, your subscribing, and your thoughtful comments give life to this channel, just as blood circulates through the body and keeps a human being alive. Without you, this channel would have no heartbeat and no purpose. I thank you all from the bottom of my soul, and I send you my love, respect, and appreciation as we continue this adventure together. Many people imagine that the night sky is a perfectly clear open canvas where all objects, big or small, glow brightly and reveal themselves to any telescope pointed in their direction. In reality, the truth is far stranger and far more unsettling. Space is filled with objects that do not cooperate with our expectations, and among them are asteroids that remain hidden until the final moments before they pass Earth, or even graze our planet. These unseen travelers challenge every assumption we have about how the universe reveals itself, and they remind us that the darkness of space is not empty. It is full of secrets slipping quietly beyond the reach of human eyes. Astronomers have built incredible systems to survey the heavens, but even the most advanced telescopes miss objects that by all logic should appear clearly. This script explores in great detail the reasons behind this strange phenomenon. The invisibility of some asteroids is not magic, and it is not a failure of technology alone. Instead, it is a perfect storm of physics, chemistry, geometry, motion, and cosmic coincidence. Each paragraph draws you deeper into the unseen realm of celestial objects that glide past the planet without leaving even a hint of their presence until they choose to reveal themselves. One of the primary reasons some asteroids are invisible lies in their composition. Many asteroids are made of carbon-rich materials that absorb almost all light that falls on them. This makes their surfaces as dark as coal, or even darker. Such objects reflect so little sunlight that they practically vanish against the vast background of space. When a telescope scans the sky, it searches for points of light. But how do you find an object that does not shine at all? The darkest asteroids reflect only a tiny fraction of the sunlight they receive, and this fraction is often too small to be detected by the scanning systems currently in use. Even when a telescope is pointed directly at these objects, they blend into the blackness like ink dropped into a shadow. The shape of an asteroid also plays a role. Unlike planets, which are mostly spherical, many asteroids have irregular forms full of deep ridges and uneven faces. When these surfaces rotate, the amount of light reflecting off them changes dramatically. Sometimes a reflective surface turns toward Earth, and the asteroid briefly brightens. At other times, a dark facet appears, and the object seems to vanish completely. If a telescope happens to observe the asteroid during one of these dark phases, the detection system may conclude that nothing is there. This creates an illusion of disappearance, even though the asteroid continues to move silently through space. The combination of irregular shape and slow rotation makes some of these objects nearly impossible to track consistently. Another issue is the angle of approach. Many people assume that asteroids approach Earth from the front where sunlight illuminates them clearly. But some approach from the direction of the sun. When this happens, their sunlit sides face away from us, and their dark sides face toward Earth. A telescope cannot look directly toward the sun without destroying its sensors, so any object approaching from that direction moves unseen. This solar glare blind spot is one of the most concerning areas of sky monitoring because it hides objects until they are extremely close. Several past near misses have come from this region, catching astronomers by surprise and reminding us of the limitations of even the most vigilant sky surveys. Distance is another critical factor. The farther an asteroid is from Earth, the dimmer it becomes. Most telescopes can detect bright objects at tremendous distances, but faint dark objects must be much closer before they can be seen. By the time these dim asteroids come close enough to be visible, they may already be moving rapidly past Earth. The discovery often occurs only hours or days before the closest approach. If the object is small or moving quickly, it may escape detection entirely until after the event. This raises concern among scientists who study planetary defense, because understanding the orbit of an object is essential to predicting its future path and potential hazard. Motion itself complicates detection. Telescopes search the sky by capturing images at regular intervals. Automated systems look for points of light that change position between images. But if an asteroid moves too fast, it may appear as a streak rather than a point, and streaks are sometimes ignored or dismissed as noise. Conversely, if an asteroid moves too slowly or is heading almost directly toward Earth, it may not change position enough between images to be detected. In both cases, the system fails to recognize the object even though it is present. This is one of the most counterintuitive aspects of asteroid detection. Too fast or too slow both lead to invisibility. Another reason asteroids remain unseen is that many are incredibly small. Size matters greatly because the amount of sunlight an object reflects is proportional to its surface area. A tiny asteroid only a few meters wide reflects so little light that even a bright surface would be nearly invisible across long distances. And many small asteroids are not bright at all. These tiny bodies are still dangerous because their speed provides significant impact energy. Although small objects burn up in the atmosphere, the largest among them can still cause local damage. The challenge is that small objects are more common than large ones, and every one of them is far more difficult to track. Space is also filled with background noise that interferes with detection. Cosmic rays, dust reflections from satellites, and even distant stars create confusing signals. Detection software must separate true moving objects from countless tiny sources of fluctuation. A faint asteroid that blends into this noise may be missed simply because the system has no way to distinguish it from the natural background. This problem becomes more significant as telescopes become more sensitive. The more they detect, the harder it becomes to identify which signals represent real nearby objects. Light pollution on Earth contributes as well. Ground-based telescopes must contend with city lights, atmospheric distortion, humidity, and even moonlight. All of these factors reduce visibility and create conditions in which faint asteroids can go unnoticed. Even telescopes placed in remote desert locations or on mountaintops cannot escape these limitations entirely. The atmosphere bends and scatters light, making faint objects easier to lose in the visual clutter. Space-based telescopes help significantly, but they are expensive, rare, and limited in number. Another factor is the unpredictability of asteroid surfaces. Some asteroids eject dust or gases that create a dim haze around them. This haze can change their brightness unpredictably, making it even harder for detection systems to maintain consistent tracking. If a telescope records the asteroid when it is slightly brighter, it may be cataloged and tracked. But if the next observation occurs during a dim period, the asteroid may seem to vanish. Such objects are labeled lost, and astronomers must wait for them to reappear, sometimes years later. Many asteroids hide within the cluttered regions of space, such as the galactic plane, which is full of stars, gas clouds, and distant galaxies. Searching for a faint dark object against this crowded background is like searching for a grain of black sand on a beach at night. Some survey programs avoid these busy regions because the risk of misidentifying objects is too high. But that means any hidden asteroids traveling through these regions remain unseen. And because their orbits eventually bring them back toward Earth, they continue to represent an invisible threat. Micrometeorite impacts and surface aging also change the reflectivity of asteroids over time. An asteroid that was once relatively bright can become darker after space weathering. As solar wind and micrometeorites bombard the surface, the minerals become chemically altered and begin to absorb more light. The longer an asteroid travels through space, the darker it becomes. Over millions of years, even metallic surfaces can lose their shine, becoming dull charcoal-colored bodies that swallow light instead of reflecting it. Another surprising factor is that some asteroids rotate in chaotic, unpredictable ways. Instead of spinning smoothly, they tumble erratically. This chaotic motion means their brightness fluctuates rapidly, making it harder for telescopes to capture consistent measurements. A sudden dimming during a scan can cause detection software to lose the object entirely. Tumbling asteroids also introduce uncertainty in orbital calculations, since their uneven shape affects their motion through a subtle force known as the Yarkovsky effect, in which sunlight gently pushes the asteroid over long periods. This push changes their path, unpredictably adding to the difficulty of tracking them. The stiffness of our detection schedules also plays a role. Telescopes cannot scan every region of sky every moment. They follow planned sequences and priorities. A faint asteroid passing through a region during a time when the telescope is not pointed there is simply not recorded. Sometimes an object is detected once, then missed in the next, leaving no way to confirm its presence. Without multiple detections, it cannot be added to catalogs, and its orbit cannot be calculated. As a result, it enters the category of lost objects, silently drifting until it either reemerges or disappears forever. This challenge becomes even greater when the asteroid travels through the twilight zone, the area of sky near the horizon just after sunset or before sunrise. The bright glow of scattered sunlight washes out faint objects, and telescopes avoid pointing too close to the horizon to prevent distortion. Many discovered asteroids that approached Earth from this region were detected only when they entered clearer skies. But countless others are suspected to pass through unnoticed. A further complication is that some asteroids reflect infrared wavelengths more efficiently than visible light. If a telescope only observes invisible wavelengths, it may miss these objects entirely. Infrared telescopes can detect them by sensing their heat, but there are very few space-based infrared observatories. Most surveys rely on visible light, which makes infrared bright, but visible dark asteroids effectively invisible in the most common observations. Even the way software interprets data can hide asteroids. Automated detection systems are trained to identify patterns that resemble known asteroids. But objects that behave differently, such as those with unusual motion profiles or erratic brightness patterns, may be misclassified as noise. This means advanced artificial intelligence systems sometimes overlook exactly the objects we most need to detect. Scientists continue to refine these systems, but the challenge persists. Another reason some asteroids disappear is simply the vast scale of the sky. Even with many telescopes scanning millions of stars in countless regions, each night the sky is too large to monitor completely. Some asteroids slip through gaps between scanning zones. Others appear in regions that receive fewer observations because of instrument limitations. Until more telescopes are deployed and coordinated globally, these empty zones will continue to hide objects. Solar radiation also creates unpredictable brightness fluctuations. When charged particles strike an asteroid, they can cause temporary brightening or dimming. These irregular changes create noisy signals that confuse detection systems. A single burst of brightness may be misinterpreted as a star or satellite glint. Without consistent detection across multiple nights, the object cannot be confirmed. Another important factor is that some asteroids are covered in porous material, such as loose dust or regolith that absorbs sunlight instead of reflecting it. This soft, fluffy layer acts like a cosmic sponge, soaking up light and making the object extremely dark. Telescopes expect solid surfaces that reflect at least some light. But these dusty asteroids resemble cold shadows floating through space. Long-period asteroids that spend most of their time far from the sun present another challenge. While they're distant, they remain incredibly faint. Only near their closest approach do they brighten, but if they approach from a blind region or during unfavorable observational conditions, they may still remain unseen. These long, wandering objects represent some of the greatest unknowns in planetary defense, because their appearance is unpredictable and they may only be discovered upon arrival. The Earth itself creates blind spots as it blocks a portion of sky at any given moment. Telescopes on one side of the planet cannot observe objects hidden behind Earth. Coordinated global monitoring helps reduce this issue, but there are still moments when coverage gaps occur, especially when weather blocks multiple observatories simultaneously. Human limitations play a role as well. Astronomers must decide which regions to prioritize based on statistical models. These decisions guide telescope schedules, but models can be wrong or incomplete. If an asteroid takes an unexpected path, it may pass through a region not currently prioritized for observation. This possibility is one reason astronomers constantly update their models as new data becomes available. But the updates take time, during which unseen objects continue their travels. All these challenges combine into a single conclusion. The invisibility of some asteroids is not due to one single factor, but a complex web of cosmic and technical limitations. Every hidden asteroid is a reminder of the vastness of space and the limitations of human technology. Yet scientists continue to improve detection systems with new wide-field telescopes, faster software, and space-based observatories capable of scanning regions impossible to see from Earth. Each improvement uncovers new objects, many of which have been passing quietly for decades. Despite the risks, the study of hidden asteroids also inspires awe. These objects travel along ancient paths shaped by the formation of the solar system. They carry clues about the early universe and the materials that built planets, including our own. Understanding them is not only a matter of planetary defense, but also a journey into our cosmic origins. Every discovery reveals a piece of the story written in the silent, drifting stones that wander the solar system. As we continue to peer deeper into the darkness, we must accept that the universe does not reveal all its secrets at once. Some remain hidden, waiting for the right moment, the right telescope, or the right scientist to uncover them. Until then, the invisible asteroids serve as a humbling reminder that we live in a dynamic, moving universe full of unseen travelers passing by Earth every day. With each new detection, we illuminate another corner of the cosmic ocean, reducing the unknown and strengthening our understanding of the celestial neighborhood we call home. Dear audience, as we reach the end of this video, I once again want to express my heartfelt gratitude for staying with me until the final moment. Your time, your presence, and your support turn every video into something meaningful and alive. You're the reason this channel continues to grow and shine. Your likes, your comments, your shares, and your subscriptions are the energy that keeps this journey moving forward, just as the heartbeat keeps a person alive and strong. I'm truly honored to have such a warm and supportive family here. Thank you for your kindness, thank you for your dedication, and thank you for allowing me to be a part of your day. I love you all, and I look forward to meeting you again in the next video, where we will continue exploring, learning, and discovering together.